Transparent Physics presents Noobster Class Adding Two-Dimensional Vectors, Lesson 2, Right Triangle, Wrong Answer. Our objectives in Lesson 2 center around some more fundamental math skills. Specifically, we're going to be working with right triangles. We're going to discuss how to find an unknown side of a right triangle using the Pythagorean Theorem. We're going to use SOHCAHTOA to solve for the missing part of a two-side one-angle combo on a right triangle. And also we're going to try to warn you about some potential errors that are commonly found among new mathematicians of right triangles. I don't know, sometimes on TV you'll see a car commercial and there's like a guy dressed up in an Einstein mask pretending I'm a professor of savings, and then on the background chalkboard they'll have a couple equations scribbled. One of them will of course always be E equals mc squared. And the second one you almost always see is the Pythagorean Theorem. So let's talk a little bit more about that, see what it actually means. You can see we've got a right triangle. Again, we have to have right triangles in order to use the Pythagorean Theorem. And there's a side A, a side B, and a side C. And for the side C, that's known as the hypotenuse. It's the longest side. And it's the side sort of oppositely positioned with respect to the 90-degree angle, the corner in the right triangle. So you have this relationship a squared plus b squared equals c squared, where a and b are the length of the two legs, and then c is the hypotenuse. And then it doesn't matter which side is a and which side is b, but the hypotenuse always has to be side c. So in order to see this in action, let's set up a sample problem. We've got a right triangle with two legs, one 8 meters and other side 14 meters, and we don't know the hypotenuse. It is a right triangle, and the side opposite the 90-degree angle is the hypotenuse. And we want to solve for that hypotenuse. So we start with the classic equation, a squared plus b squared equals c squared. I just flip the left side and the right side around, that's free, just to put the unknown on the left side that we're going to be solving for it. And then we want to get c by itself. C by itself just means you take the square root of both sides. So c squared, square root of c squared is just c. And then you take the square root of a squared plus b squared. Plug the measurements in. I'm always a big advocate for keeping the units with your measurements so you can make sure everything works out properly. So when you square 8 meters, you get 64 meters squared. Under the square root is a meter squared plus a meter squared plus meter squared still gets you meters squared, as it shows, but the square root of meter squared gets you meters again. So the units do work out, and you get around 16.1 meters. Little fast fact, the hypotenuse always has to be the longest side of the triangle. So if you're solving this out and you notice that the hypotenuse is not the longest side, you might as well try to figure out what the error is before your professor or teacher does. As far as Pythagorean theorem problems go, there's really not much they can throw at you. You're either solving for the hypotenuse or you're solving for one of the legs. So let's solve for one of the legs then. So we're going to solve for the missing leg. We know the hypotenuse already is 400 meters. One of the sides, the smaller side, is 240. So we're going to solve for the missing leg. The missing leg is going to be more than 240 and less than 400. What exactly does it end up being? Let's find out. So in this case, again, it doesn't matter which one is A and which one is B. So we'll just arbitrarily say, okay, we're solving for B. In order to solve for B, we subtract a squared to the other side to get b squared by itself. Now b squared is not technically solved for yet because we want b, not b squared. So we take the square root of both sides. And so then we have b equals the square root of c squared minus a squared. Plug in your values. Again, I like to keep the units with everything. Notice that we have a meters squared under the square root, which means we're going to have meters when we're done. And the answer ends up being 320 meters. So that fits right within our range that we estimated it would be to start. So there's a movement afoot called the minimalist movement, and the minimalist movement wants to downsize and simplify and get rid of all the possessions that are dragging you down, not building you up. And I feel that minimalists would be very impressed with SOHCAHTOA because SOHCAHTOA has 3 different mnemonic devices, or a single mnemonic device for 3 different equations. And it's all based around the idea of a right triangle, and it focuses on one angle that's not the 90-degree angle in one of the other corners of the right triangle. So for example, if we have this triangle here, if you notice, it's going to be the same triangle printed twice. If the upper corner was the one that we were sort of more interested in, and we knew the angle for that corner, or we were interested in solving for the angle of that corner, with respect to that corner, the side of the triangle opposite that is logically called the opposite side. I tell people that if you were standing in the corner with the angle and you like threw like a lemon or something, the side of the triangle that it would hit opposite you is the opposite side. The hypotenuse is always the hypotenuse. It's always opposite the 90-degree angle. And then the adjacent side is the leftover side, but you also want to remember that it's the side that's adjacent or next to the angle in question. The hypotenuse is also adjacent to the angle in question, but the hypotenuse is always the hypotenuse, so we don't need any special rules for that. Now the triangle below that first triangle is an identical triangle. It's the exact same triangle. But what if instead we looked at the angle in the lower right corner, and there's no reason we couldn't do that. Now, since the angle has switched, the opposite side is also going to switch, because if I throw a kiwi fruit, it's going to hit that side instead of the side from the previous triangle. The hypotenuse is always the hypotenuse. And then now the adjacent side is the side that's remaining that is close to the angle, but not the hypotenuse. Exact same triangle both times, but the adjacent and opposite side changed based on where your angle in question was. And now that we've defined angles and the side names, we can reveal the 3 trigonometric formulas that show how 2 sides of a triangle relate to an angle within that. So anywhere that it says theta, that's one of those 2 corners that's not the 90-degree angle. And then basically, each trigonometric identity links to 2 of the 3 sides. So you've got a trigonometric identity, 2 sides of the triangle, and you can match the information you know to the formula to solve for a 3rd piece of information. So if you had 2 pieces of information, you can solve for the 3rd. And again, it's important to know which angle you're looking at in the triangle, whether it's the upper one or the lower one. And again, that depends on the orientation of the triangle as well. Now, the math associated with SOHCAHTOA tends to be a little bit more confusing to students, especially because we're now dealing with these trigonometric identities, sine, cosine, and tangent. We'll just pick a random one to start. It doesn't really matter which one you use. The procedures are the same for manipulating it. But let's say we have, we're given an angle inside of a right triangle, and we're given one side, and we want to solve for a different side. So let's say, for instance, with this first scenario, that we are given theta, and we are given the hypotenuse, and we want to solve for the opposite side. So if we want to solve for the opposite side, we want to get the opposite by itself. Since opposite is divided by hypotenuse, you multiply both sides by hypotenuse. Then the hypotenuse on the right-hand side cancels out. Hypotenuse on the left-hand side finds a new home, and we just flip it around to get the unknown variable by itself. So the opposite, the length of the opposite side, is equal to the length of the hypotenuse times the sine of theta. If instead we had the same starting equation, but we were interested in solving for the hypotenuse instead, the solving for the hypotenuse actually starts off the same way. It is always my recommendation that if you have some variable in the denominator and you need to solve for it, get it out of the denominator. Just bring it up out of there. You'll be much less likely in most cases to make mistakes moving forward. So we have the exact same step we did before. It doesn't seem like we're getting any closer, but now we can try to get the hypotenuse by itself by dividing both sides by the sine of theta. And when we do that, we can see sine of theta ends up in the denominator on the other side. So we now have an expression to solve for the hypotenuse should we know the opposite side and the sine of theta. while the previous slide offers a little challenge to maybe those that aren't as familiar with trigonometric identities, sine, cosine, and tangent, actually solving for an angle itself is very confusing to students who don't have a strong background or a background at all in trigonometry. But what we want to remember is that sine is just a mathematical procedure. If we wanted to get rid of a square root, we would square something. If we want to get rid of a sine, we take the inverse sine. So we take the inverse sine, and so sine -1 times sine cancels each other out. But if we take the inverse of sine on one side, we have to take the inverse of sine on the other side. And we end up with theta is the inverse of sine times the quantity opposite over hypotenuse. And we'll, when we get in a little more detail on the math side, I can show you guys how to calculate the inverse sines and inverse cosines and things like that. They're not super hard to do. It's just, I mean, if you can take a square root and a square, you can probably take a sine and an inverse sine. Okay, we've reached that time in the video for an obligatory tea break, and let's just make that happen. All right, good. So while I was doing research for this lesson, I stumbled onto something that I thought was pretty interesting, so we'll share it during the tea break today. So the ancient Indian astronomer, and I apologize, he was an astronomer and a mathematician, Aryabhata. I couldn't tell you exactly how that's supposed to be pronounced. The first, he studied astronomical events, and he was tracking the sun as it sort of rose above the horizon on what he assumed was a circular path. And so he had a term that he used that was an abbreviation for the height of the star as part of sort of the circular path that star travels, and he referred to it as a JYA. Now, later, the Arab science and math communities really did a bang-up job in preserving scientific and mathematical texts from all over the place. And so when they were translating Aryabhata's work into Arabic around the 10th century, they converted it to the phrase JIBA instead of JYA. So it's sort of like a little bit of a game of telephone. It changes a little bit with every go. And what happens is when the scribes were recopying texts, they often dropped vowels just as a way to sort of speed things up. And I don't know, sort of like taking concentrated orange juice or something. Yeah, they just minimize what they have to write because it wasn't a printing press at the time. It was actually physically people writing. So the more efficient they could be about it, the better. So JYA became JIBA, which became just JB. And the funny thing is that later, when they were trying to sort of reconstitute that back into a real word by adding vowels to it, JIBA isn't actually a word in Arabic. So they interpreted JIB instead as JIAB, which is Arabic for cove or bay, sort of like a body of water near the shore. And so when that was then converted to Latin, they used the Arabic word for cove or bay as the base word. So the term JAIB became sinus, which is Latin for bay. And you can probably see where this is going. And this is where we got the term sine. Our term sine in trigonometry is based on this century-long game of telephone, where the meaning changed a little bit and changed a little bit and changed a little bit and changed a little bit. But that's why we call it sine. So, fun fact, share it with your math teacher. I just thought it was pretty cool. So, wanted to share it with you guys and gals, boys and girls. So we're going to move into just some more general examples of this in play, and a couple tips to avoid wrong right triangles. First of all, always make sure that you're actually dealing with a right triangle. Some teachers might say, well, if it looks like a right triangle, just assume it's a right triangle. And again, technically, we're not supposed to do that. If your professor says or teacher says to do it, then that's fine. But just recognize, they should always be specifically designated as a right angle in order to use these formulas. Another common mistake is that some calculators, especially the fancier like graphing calculators, have a default setting when you're dealing with angles to have a unit called radians, which is great for other things, but not really for what we're doing right now. So make sure you switch out of radians into degrees when you're solving this out. It's nice to just draw a quick sketch, and it doesn't have to be perfect, but if you roughly scale it to the information that's given, that'll give you a sense of what you would be looking for an answer, especially as a newer calculator. It helps to know sort of what you're going to be ending up with, so you have something to compare your answer to. Make sure you are careful about setting your opposite and adjacent sides based on the angle, not just a angle, and definitely not the right angle either. And finally, and this is easier said than done if you don't have a very strong trigonometry background at this point, but sine, cosine, and tangent are just mathematical operations. No different than taking a square or a square root. So we can undo a square, we can undo an addition, we can undo a subtraction, and we can undo a sine, cosine, or a tangent too. Okay, so if we take a look at this, practice problem number 1, we have 2 legs of a right triangle, and we're solving for the hypotenuse, the missing side. So we have the formula a squared plus b squared equals c squared, similar to the sample we worked out before. Manipulate it to solve for c by taking the square root of both sides, and then we can plug in our values. So you get 10 meters squared plus 25 meters squared ends up being 725 square meters, and taking the square root of that is around 26.9 meters. So a pretty basic example of Pythag for us. Here's another right triangle where we have to solve for a missing side, but if you take a look at the information that's given here, we don't have 2 sides. We have a side and an angle. So anytime they give us an angle, and again remember the 90-degree angle doesn't count, that's just sort of gets us in the door. Since we know there's an angle involved and we have one side, we're solving for the hypotenuse. So if we're solving for the hypotenuse, we want to find an equation that has h in it for our fraction. And we also want to note the fact that the 30-degree angle is adjacent or next to the 450 meters. So we are looking for a formula that includes the adjacent variable and the hypotenuse. And in order to solve for this missing side, we're going to use the cosine of theta equals the fraction of adjacent divided by hypotenuse. So we're interested in getting the hypotenuse by itself. Again, since it's in the basement, let's get it out of the basement first, isolate it, then get rid of the trigonometric identity. So hypotenuse is by itself. So we multiply both sides by hypotenuse, divide both sides by the cosine of theta, and we're good to go. So the hypotenuse is the adjacent magnitude divided by the cosine of theta. Plugging in those values, we get around 520 meters. And it's longer than 450, which it should be. So that's nice that that works out that way. All right, setting up this next problem, we have one side of a triangle is 12.1 meters. The other side of a triangle is 17.1 meters. That's going to be the hypotenuse, 17.1 meters, or the C side, depending on how we want to think about it. There's no angle specifically referred to. You might say, that looks like it's a 45, 45, 90 triangle. And I mean, again, you could be entirely right, but you can't assume that without knowing something more about the angles or values or something. So we are interested in solving for the unknown side. So in order to solve for the unknown side, we're going to start with the Pythagorean Theorem because there are no angles of interest at the moment. Manipulating to solve for one of our unknown legs, taking the square root, plugging in the values, and getting a final answer of around 12.1 meters. So 12.1 meters and 12.1 meters, if your instinct said that looks a little bit like a 45, 45, 90, you were right. But again, it doesn't take much for it to be off by a couple degrees, depending on what sort of starting information you have. So just be careful when you're solving these out. Don't make assumptions. Let the equations tell you where to go. Okay, practice problem 4. This will be the last one, and in what is probably in the running for the worst set of taglines for a movie. No more sides. Time to find an angle. So in the comments, go ahead, name the movie to which the movie poster would have those taglines on it. So we've got a right triangle, even though it doesn't look extraordinarily like a right triangle. It's got the right triangle square in, so totally legit. And based on what we know, we have an angle that we're solving for, and we have 5.6 kilometers, 3.2 kilometers. Looking at that orientation, the side that we don't have any information about at all is the hypotenuse. We are not asked to solve for it. We don't know it. We know the opposite and adjacent sides. So since we know the opposite and adjacent sides and we're solving for an angle, that tells us to use the tangent of theta equals opposite over adjacent. Now the opposite, based on the angle that we are given, the opposite is 5.6, the adjacent is 3.2. So we're going to first solve for the angle. Tangent of theta is not the angle. That is still a mathematical operation performed on the angle. So we got to get rid of our tan by taking the inverse tan. So we take the inverse tan of both sides, and we're left with theta all by itself. Theta is equal to the inverse tangent of the opposite over the adjacent. And when we plug that in, the opposite is 5.6, the adjacent is 3.2. Plug, chug, and your calculator gives you approximately 60.3 degrees. And looking at the triangle again, you can see that the opposite side is longer than the adjacent side, which is going to pull that angle past 45 degrees. So 60 degrees seems like a reasonable answer based on the sketch that we drew. Okay, we got a quick closing thought here. I know some of you people are probably thinking, hey, I signed up for this course to add two-dimensional vectors and I'm just doing like basic math stuff. Well, yes, but knowing how to work with right triangles is extremely important to the process. We're going to be using right triangles to sort of connect us between the vectors we're starting with, which could be pointing anywhere, and the resultant vector that we want to end up with. As always, if you found the content of this video helpful, feel free to hit the like button. Probably the story about the naming of sine is worth the price of admission just by itself. If you have any questions about anything discussed in this lesson, feel free to leave it in the comments section. And to be informed of what's coming next from Transparent Physics, please consider hitting the subscribe button. Thanks for sticking around to learn a little bit about right triangles. Hopefully, I've made things a little clearer for you on this lesson from Transparent Physics.